Hello, we are back for round number 2 for chapter 6. We're going to start talking about using those balanced equations for stoichiometry. So stoichiometry is how we use balanced equations to find amounts of the chemicals that we need. So this would be very important if you're trying to order chemicals for a laboratory, or you're trying to figure out how much of each one you need to add to make a certain amount of product. Chemicals can be dangerous for our environment. They can also be extraordinarily expensive. So we have to make sure that we're not overspending and ordering way too much or ordering far too little and having to pay shipping costs twice as well as be waiting for a chemical to come in the mail. So we have to make sure that we know how much we need. And this is just a recipe, right? So if we're going to make something, we need to go to the store and we need to buy what we need. But I don't need to buy 20 pounds of flour to make 6 dozen cookies. I only need to have 2.5 cups, so I can buy a smaller bag of flour, right? So we're going to be looking at these as our chemical recipes. So how do the amounts compare? We're going to be using and looking at the coefficients that we just put in front of them. So now that we have balanced this equation, remember when we balance, we can only change coefficients. We can't ever change subscripts because subscripts are what makes it that compound, the ratio of those elements together. So we've changed coefficients and we've made a balanced recipe, a balanced chemical recipe or a balanced formula. Excuse me, chemical sentence. So here we have the amounts that go in. So we're going to look at these coefficients of this to get what we need. So this would say I need 2 moles of ammonia for every 1 mole of carbon dioxide. But remember, we can't really order moles. We need to convert that to something that is measurable in the lab. So we would convert that to grams and figure out what we need for a certain amount of product that we would like. So how much do we have? So in this case, I have 4 moles of ammonia, 5 moles of oxygen, 4 moles of nitric oxide, and 6 moles of water. So 4 moles of ammonia, 5 moles of oxygen, 4 moles of nitric oxide, and 6 moles of water. Let's write some what we are going to call mole ratios. So mole ratios are just what are the ratios of each of these compounds to one another. So I'm going to put these in their per expressions. So if I need 4 moles of ammonia for this to work, I would need 5 moles of oxygen. Now I can write this either way. I can say 5 moles of O2 for 4 moles of ammonia. This is going to be a per expression, just like I've been harping on you all year that it's grams per mole, grams per mole. These are going to be used as conversion factors. So that's why this is going to be so important for us. It's going to allow us to convert from one compound to another. So that's how we can say, if I have 10 grams of ammonia, how much water can I produce? How many grams of water can I produce? This is how we're going to do that. We're going to use these ratios to tell us that exact answer. So those are some mole ratios. So 5 moles of oxygen, we would produce 4 moles, running out of space, of NO. So that's how we would go between them. Okay, so let's balance the equation. So let's balance this equation together. We're going to have 2 carbon on this side, 4 hydrogen, and 2 oxygen. Over here we have 1 carbon, we have 2 hydrogen, and we have 3 oxygen. So I'll put a 2 here, that makes this a 2, and that oxygen goes from, so 2 times 2 is 4, plus 1 is 5, so this goes to a 5. 2 carbon, 4 hydrogen on the left, 2 hydrogen on the right, so I need a 2 here. That's going to change that to a 4, and I'm actually going to pull the eraser up right now. Erase that so I don't get confused or run out of room. So I have 2 carbon. I have 2 times 2 is 4 oxygen plus 2 on the other one, so that's 6 oxygen. And I have 4 hydrogen, 2 times 2. So now everything except the oxygen is balanced. So if I go over to the left, I have 2 oxygen, and on the right, I have 6. So I need 3 of these because that will make this into 6. Just to double check, I have 2 carbons, 4 hydrogens, and 6 oxygens on the left. I have 2 carbons. I have 2 times 2 is 4 hydrogen, and 2 times 2 is 4, plus 2 is 6. So this is balanced. In order to do any type of stoichiometry, the first step is always balance the equation. So you must start with a balanced equation. If you don't, then you don't have a balanced recipe and you won't get cookies, you'll get something else. So you won't get the products you want if you don't use a balanced chemical equation. So this is how we relate moles of one thing to roles of another. So remember, this is a 1, just because it's not written there. We don't write 1s in chemistry. So I would need 1 mole of C2H4 per 3 moles of oxygen, or you can write that as 1 mole of C2H4 for 3 moles of O2. Remember, we can write them in any way. We can use it. We're going to follow our unit you want to get rid of goes on the opposite location, and then the unit you want goes on the top. Or, well, if you want it in the numerator, right? If you want it in the denominator, it would have to go in the opposite place. So that's our simple algebra way of looking at that. So we are going to be using our factor label method, or what we call dimensional analysis. Okay, I'm going to erase some of this so I have some room to write some more per expressions. So we would have 3 moles of oxygen per 2 moles of CO2, 2 moles of CO2 per 2 moles of water, 2 moles of water per 3 moles of O2, and we can write those all opposite too. So 3 moles of O2 per 2 moles of water, and so on. So you can write them in any which way. Let's see, do we have CO2 oxygen? We'll say 2 moles of CO2 per 3 moles of O2. So it just depends on which way we're going. This one and this one are opposites of one another. So if we're going to oxygen, we would use this one. If we want to get rid of oxygen and go to carbon dioxide, we would use this one. So that's where it depends on which one we use. Now, this is our balanced equation that we just balanced on the previous page. We're going to do some stoichiometry with it. So how many moles of CO2? So or how many moles? We always write the information underneath the equation because this becomes a story problem and we're going to have to extract the information. So how many moles of CO2 are formed by burning 5.30 moles of C2H4? So we're going to start always with what's given. So this is the number that's given, 5.30 moles of C2H4. Multiplication sign and a line. We put the unit we want to get rid of in the opposite place. So this is in the numerator. So we're going to put this in the denominator. So we put moles of C2H4 in the denominator. And the numerator, we want to go to moles of CO2. So we're going to put moles of CO2. How do we exchange between moles? Well, we look at the balanced chemical equation and we look for the coefficients. So there's a 1 here and there's a 2 here. So I put the 1 next to C2H4 and the 2 next to CO2, and I do the math because this unit cancels and I'm now in the unit that was requested, moles of CO2. So our calculator should give us this. It probably only gave you 10.6, but 10.6 is actually the significantly figured right answer. So 10.6 moles of CO2, number, unit, and label for a proper answer. Now I want you to try the next one. So I want you to try this one again. We have already balanced the equation. Try this one, so pause it and then try it. So we are going to get this one by saying how many moles of oxygen, so how many moles of O2 are needed to form 0.242 moles of H2O. So we always start with the number that's given, 0.242 moles of water. Now right now it's a little simple because we're only given one number. Eventually we'll be given more than one number. I want to get rid of moles of water. The moles of water I have right now are in the numerator, so I need to put that in the denominator. So moles of H2O, how many of those? And then I need on top moles of oxygen. So I'm going to look up here. For water, it's a 2. And for oxygen, it's a 3. So I put those in their respective places. My unit here is canceling because they're in opposite locations. I multiply across the top and I divide by what's on the bottom. And I get 0.363 moles of O2. And 3 sig figs here and 3 sig figs here make this an appropriate answer. Right, we can give this one a try, but you haven't done grams yet, so if you want to wait or try this one together, that's okay. How many grams of CO2, so how many grams of CO2 formed by burning 0.739 moles of C2H4? 0.739 moles of C2H4. Where do we start? With the 0.739 because we have that. We can start there. We have to start somewhere where we're given a number. 0.739 moles of C2H4. Multiplication sign and a line. Oh, we want to get rid of moles of C2H4 and go to CO2, but we're asked for grams of CO2. Can we go directly from moles of C2H4 to grams of CO2? And the answer is no. First, we need to go from moles of C2H4 to moles of CO2. And then we use molar mass to go, this is mole ratio. We use molar mass that we know how to calculate to go from moles of CO2 to grams of CO2. So that's going to be our pathway. So we get rid of moles of C2H4, that's a 2, and we go to moles of CO2. So those numbers come from our balanced chemical equation, a 1 and a 2. Now my moles of C2H4 cancel. I'm in moles of CO2, that's not what was requested. I need to go to grams. So every 1 mole of CO2 has a molar mass of 44.01 grams of CO2. And where did I get that from? Well, that one was in my head. It won't be in your head. You'll have to calculate it from a periodic table, just like we've been doing since test number 1. So you got this, you can do it. We multiply across the top. So 0.739 times 2 divided by 1 times 44.01 divided by 1. And we end up with 65.04678 grams. 3 sig figs here. So we can only have 3 sig figs in our answer. 65.0 grams of CO2. So this is where our labels are very important because we need to make sure that we made it to CO2 like the question asked us to do. Because if we're still in C2H4, we did something wrong. All right, next up, same equation, give this a try. Pause it, try it. So this is similar to the one we just did. Give it a try. How many moles of oxygen are used to form 43.7 grams of water? So we're going to start with the 43.7 grams of water. So we're going to start with grams of water. To go from grams, you need molar mass. To go to moles of water. Because once we're in moles, the world is our oyster and we can do anything we want. Then we use the mole ratio to do what is requested and go to moles of oxygen. So moles of oxygen. So if you couldn't figure it out before, now that you have the pathway, give it a try. So 43.7 grams of water times grams of water goes on the bottom, and 1 mole goes on the top. Remember, molar mass is always for 1 mole, and this is 18.016 grams. So grams of water cancel. I need to go now from moles of water to moles of oxygen. So looking at the balanced equation, that is a 2 and that is a 3. So the 2 goes with water and the 3 goes with oxygen. And I'm going to say 43.7 times 1 divided by 18.06 times 3 divided by 2 gives me 3.638432.504 moles. 3 sig figs in your answer. So 3.64 moles of O2 are going to be what form? Hopefully this is going well for you. Let's try the next one, which is going to bring up a question about limiting reactants. So this is going to give you some terms that you need to learn. One of the items is always going to limit us from going forward. So let's say our recipe calls for 2.5 cups of flour and 1.5 cups of sugar, 2 eggs. Don't make this, I have no idea. All right. We would want to say, if I have 5 cups of flour and I have 3 cups of sugar and 3 eggs, can I make this recipe twice? No, because I'm going to run out of eggs. In order to make it times 2, I would need 4 eggs. So the recipe won't turn out the same. So I can only make 1 times the recipe. So what is my limiting reactant? Eggs. I'm going to run out of eggs. So I can't make more cookies. They won't taste like cookies if you don't use enough eggs. They'll taste like something else. So we want to make sure if we're making cookies, they taste like cookies, right? If we're going to waste the calories, it better taste good. All right, so what we're going to do is look at how to make sure, or how to figure this out. So far, we've only been given 1 number to start the problem with. Now we're going to be given 2 numbers, and we're going to be asked about a product. So here's another example with tires. So limiting reactant is going to be whatever you run out of. So whatever runs out first and stops the reaction from going forward. It limits it. It stops it from going forward. Once it's gone, there is no more of that product's reactant, so you can't make any more product. Now, excess reactant is going to be what is left over. We always want to limit that. We always want to stop the reaction as close to them being equal as possible, because we don't want to have waste. Waste is usually bad, and it is not good for the environment, and it also wastes money. So if you have 20 tires and 30 cars that need tires, let's say they each need 1 tire, can you put 1 tire on every car? No, you're going to only be able to put 1 tire on 20 cars, because you're going to run out of what? Tires. So tires are limiting. So you don't have enough tires. So that's a simplistic example. For chemistry, we're going to have to do some math. We're going to have to be given information about the reactants and then asked about a product. So if you ever see that something is, so if we have a problem and it says it reacts with excess and then of something, they're telling you that that's the excess reactant. They're telling you it's excess reactant, that you don't have to do the math to figure it out. So giving you that information up front. How do you identify a limiting reactant problem? You are given information, usually numbers or masses or molarities. We'll talk about that in a little while, to figure out how much of that reactants you have. So of 2 reactants or more, technically you could have more. and you're asked about a product. So in this equation here, if 5 moles of hydrogen react with 5 moles of oxygen, how many moles of water can be produced? In the equation, H2 plus O2 yields H2O. So we have this equation. We want to know if we have 5 moles of hydrogen and 5 moles of oxygen, how much water can be produced? So if you had 5 moles of hydrogen, we want to get rid of moles of hydrogen. We're going to go, because we're always going to go to the question mark. 5 moles of hydrogen in the, we want to go to moles of water. We would say this is a 2 and this is a 2 from the balanced equation. So this would be 5 moles of water for every 5 moles of hydrogen that are produced. If we have 5 moles of oxygen, how much water could be produced with that? Well, this is a 1. 1 mole of oxygen will yield 2 moles of water. So this would actually be 10 moles of H2O. So with using 5 moles of oxygen, we can actually produce 10 moles of water. But this one is going to run out first. So we actually, after making 5 moles of water, we completely run out of hydrogen. And we can't make water without hydrogen. Otherwise, it'd just be oxygen. Just a lonely oxygen. And it wouldn't work. So it wouldn't be water. And it'd be highly reactive. Probably die. So wouldn't want to drink it. So in order for it to be water and have 2 hydrogens and 1 oxygen, you have to have more hydrogen because you just ran out. That's a limiting reactive problem. The terms theoretical yield. Theoretical yield, I might put this, theoretical yield, TY, is the maximum amount of product predicted by stoichiometry. Predicted by stoichiometry. Rarely does anybody get 100% of what they should get in a lab. Now, in organic chemistry, you might get over 100% because everything around us is organic, and you might have something fall into your reaction or cause it to, absorb oxygen or something from the atmosphere. So there are things that can cause it to go over 100%, but that usually means you have an impurity. So your actual yield is what you actually got, what you actually obtained. So percent yield is the ratio, excuse me. So you take actual over theoretical times 100. Guess what, folks? You've been doing this for years. You do this every time you take a test. And you want to know what you got. You take what you got, earned, over what you could have gotten, and you multiply by 100, and that's your percentage. So you've been doing this for years. This is nothing different. What did you get over what you could have gotten times 100? That's percent yield. Steps for success, we always start with a balanced equation. So I am going to have you balance every one of these. Normally I would hand out a worksheet in class and we would work these in a worksheet. So you might have to pull out a blank piece of paper, or I think I might have the worksheet up there that you can print. Identify the limiting reactant if needed, and you have to at least compare it in terms of moles. I will take it one step further and compare in terms of grams. Why am I going to do that? You're going to see that it's an extra step, and if you're good at math, you can stop at moles, compare to moles, and go to grams. But I have found in my 10 years of teaching that those people that struggle with math, which is far more people than don't struggle with math, this is just easier to go to the final answer. Because chemistry is conceptually difficult already, why make it even more difficult by putting an extra thought process in there? So I'm just going to say, let's take it all the way to grams. Whichever one is the smallest is your limiting reactant. Then you're going to convert to the desired unit. So I won't have to do this step because I'll already have done it because of that. Okay? So this is going to actually, I only have to really do 2 steps because I'm going to write the same thing I've already calculated twice. You'll see what I'm talking about when we get there. All right, so consider the following equation. Now, how do I name that copper? What is it? Copper what? Copper 1 sulfide reacts with oxygen to form copper plus sulfur dioxide. So let's balance it first. How many copper on the left? 2. 1 sulfur and 2 oxygen. I have 1 copper on the right, 1 sulfur, and 2 oxygen. So I just need to put a 2 here. And now it's balanced. Woo! So let's take a look. Let's calculate the theoretical yield. Let me erase this. I can leave it there, actually, I left enough space. Okay, calculate the theoretical yield of copper. Now I know I wanted to erase it. Because I want to write under the equation. Silly. Calculate the theoretical yield. So how much copper in grams will form when 53.2 grams of copper 1 sulfide reacts with excess oxygen. So excess, I write as XS, just because it sounds like that. So we've already been told this is our limiting reactant. This is our excess reactant. That's what this telling us the oxygen is in excess means. You don't have to do this math twice. We're going to tell you that this one's already in excess. So that's us being nice. 53.2 grams of copper 1 sulfide. Okay, we need to go from grams to moles. So we need to go from grams of copper 1 sulfide to moles of copper 1 sulfide. So we need to get our periodic table out and calculate the molar mass, which is 159.17 grams of copper 1 sulfide. Now you should be calculating these as we go throughout, so you need to practice this. So we pause it, calculate it, and then come back and check your answers. Now we need the mole ratio. So this is molar mass, mole ratio. So I have 1 mole of Cu2S for every how many moles of copper is what I want to go to is the question mark. And I have a 2. So 2 moles of copper. So for every 1 mole of copper, I get 63.55 grams of copper. So then I'm multiplying by, so molar mass times mole ratio times molar mass again, but of the different compound. That's going to be our setup for almost all of these. So when I calculate that in my handy dandy calculator, I'm going to move this down. I get 42.48112.081 grams. 3 sig figs here means 3 in our answer. So we have 42.5 grams of copper. That will form. Easy peasy. Okay, so let's balance this one. We are going to put our line here. We have 2 carbons. 3 plus 1 is 4 hydrogens. We have 1 oxygen here. That's going to cause an odd number, so we might want to write that separately sometimes, but I'm just going to add them together. 3 oxygens. And then over here, we have 1, 2 carbon. 3 plus 1 is 4 hydrogen. And we have 2 oxygen. So what do we need to do? Well, the first thing we're going to have to do most likely is, because this is an odd number, a 1, and this is a 2, we're probably going to have to put a 2 here to get rid of that that odd number because we're going to have 2 over here as well every time. So there's no other way to make an odd number even, right? So we're going to have to make that odd number even. These are some tips and tricks you pick up after doing this a bunch. So 2 of this will give us 4 carbon. 3 plus 1 is 4 hydrogen times 2 is 8. And now we have 2 oxygen in this acetate, and then we have 2 oxygen here, so that's 4 oxygen. So if we put a 2 here, we now have 4 carbon. And 3 plus 1 is 4 hydrogen times 2 is 8. And 2 oxygen times 2 is 4. So now we're balanced. So anytime you have something that's throwing it off, making it odd, and when you have even numbers everywhere else, most likely that's what you're going to have to do is change that to make it an even number by multiplying it by 2. So let's read the question and put down our information now that we have it balanced. How many grams of acetic acid? So how many grams? And now I might write acetic acid for this because I'm going to run out of room most likely on the screen. So otherwise, if I was doing this on a paper, on a test or something, I'd probably just write CH3COOH, but I might do the shorthand there because I might run out of room. Can be produced when 20 grams of CH3CHO, so 20.0 grams, is combined with 10 grams of oxygen, so 10.0 grams of oxygen. So what type of problem is this? We're given information about 2 different reactants and we're asked about a product. So this is a limiting reactant problem. What that means is we need to do 2 mass to mass problems, meaning we start with mass of one compound and we go to the mass of the product or the mass of wherever the question mark is. So the reason I put the question mark in there is because that's where you know you need to go. And so when we're going through this, you don't really have to think about it as much. I know trying to get you not to use your brain as much because it can, I'm just teasing. I want you to always use your brain, but it can really ease things up. And a lot of times people struggle with story problems. So let's just make it easier whenever we can. So starting with the 20.0 grams of CH3CHO, that has a molar mass of 44.052 grams for every 1 mole. Now we need the mole ratio, so this is the molar mass step times the mole ratio. So we're going to go from moles of CH3CHO to moles of whatever the question mark is. So the question mark here is going to be moles of acetic acid. Now we have a 2 to 2 mole ratio in that sense. Now a lot of times people ask, can I make that just 1? Technically, yes, it is 1, and mathematically your math teachers would probably want you to reduce that fraction down. I'm going to say don't touch it because it doesn't matter. You know it's 1. You can put it in your calculator. It's going to come out as 1. But there's one less point to make an error. You do not need to reduce it. Just leave it as it is. Because if you come back later and try to use that number, you might forget that you reduced it. So now I have 1 mole of acetic acid. I need to multiply that by the molar mass. So this is our general every time we do this, mass to mass. We do molar mass times mole ratio times molar mass. So we're doing the molar mass of acetic acid in this case because that's what we're going to. That's the question mark, 0.052. So my recommendation, and I know this is probably not what everybody wants to say or have you do, it's a repetitive process. So if you can get the process down and then try to really get in and understand why you're doing this, why am I going from this? It's always great to understand first. I would push that in any way, shape, or form. But if you're wondering where to start, you're confused, try to follow the units, try to follow the process and let it work for you. So this is our factor label method. We can always go from following the units. When we put this in our calculator, we should get 27.2641423 I don't know what the next number is. It's fine. That's enough. We have 3 sig figs here, so we'll only need 3 in there. So anything above 3 is fine, right? We'll start now with the 10 grams of oxygen. Oxygen is O2, so it has a mass of 32 grams per mole. So that's our molar mass step. Grams of oxygen cancel. We're in moles of oxygen, so now we can go to moles of anything. What do we want to go to moles of? Our question mark. So 1 mole of oxygen, because there's a 1 here, is going to produce 2 moles of acetic acid. And those 2 moles of acetic acid, each 1 mole of acetic acid has a mass of 60.052 grams. So you can see I'm doing this step twice. That's the one I said that was repetitive. You technically can compare at this point, but it's easier if you are struggling with math or struggling with the concept at any point. It's easier just to have this be the final answer when you're done. So this gives us 37.5325 grams. So how many grams of acetic acid can be produced? Well, if I use 20 grams, let me just do this. If I use 20 grams of acetate, I will get 27.2 grams of acetic acid. If I use 10 grams of oxygen, I could produce 37.5, but after I produce 27.3, I have run out of this material. So this reactant is gone after 27.3 grams is formed. So I can't really produce that extra here because I don't have enough of the reactant of the other reactant. So we can only produce 27.3 grams of acetic acid because this one is smaller. So you look for the smaller one. And again, that's because once we produce 27.3 grams, this one is gone and we no longer have any other reactant to combine with the oxygen. So we can't produce products if we don't have the reactants. So the next question we're going to actually go on from this is going to be how much excess reactant is left over. So you're going to need this number. You're going to need actually both of these numbers for a minute to do the excess reactant. For some reason, my forward button is not working, but that's okay. So you can see I carried over the balanced equation here for you. How many grams of excess reactant remain? So the limiting reactant was, was CH3CHO. And the excess reactant then is going to be oxygen. So on the previous page, we did this and we said that 27.3 grams could be formed when we started with 20 grams of the acetate. And if we had 10 grams of the oxygen, we could potentially produce 37.5 grams of acetic acid. So this is from the previous page. So from previous slide with 20 grams of CH3CHO and with 10 grams of O2. So same problem, just the next step. So this is a little bit confusing the way that this is going to be taught for a second, but essentially we're going to talk about what could be formed. This is what could be formed, and this is what could be formed. So if I could have formed 37.5 grams of acetic acid with the oxygen, but I only produced 27.3 grams of acetic acid, how much did I not produce? So if I subtract those, I did not produce 10.2 grams of acetic acid that could have been produced if I used all of the oxygen. So I'm trying to figure out how much oxygen that I used that was more than I needed. So I could have produced 10.2 grams of acetic acid, but I didn't. I could have produced that much more if I had enough of the CH3CHO, but I don't. So if I start with the 10.2 grams of acetic acid, That's not the answer because it's in acetic acid. I need to convert to whatever the excess reactant is, which in this case is oxygen. So I'm just going to go backwards of what I have on the previous slide. I'm going to go from acetic acid back to oxygen. So you have all these numbers already. So this is 60.052 is the molar mass of acetic acid for 1 mole. And we go from moles of acetic acid. So if I look here, moles of acetic acid and moles of oxygen, there's going to be 2 moles of acetic acid for every 1 mole of oxygen that's required. And that 1 mole of oxygen has a mass of 32 grams. So I'm just going backwards. And that equates to, my calculator says, 2.7176444708 grams. Or I used 2.72 grams of O2 remain, or they're in excess. So technically, I could have used 2.72 grams less than I used. So I could have used, 7.2, I don't know, so whatever that is, 7.28 grams of oxygen rather than 10 grams of oxygen. No, but if we're looking at this in terms that we really want this to go to completion and we want a certain amount of the acetic acid in the end, say we needed 25 grams of acetic acid, this wouldn't be too bad. It wouldn't be too wasteful. And if we're thinking about what we're wasting oxygen. Oxygen is relatively cheap. It's easy to come by. It's non-toxic. It's not going to be wasteful. So this might not be too bad to be over on this one. If we needed 25 grams, we want to make sure that this goes to completion and we're ending with 27, that might be okay because it gives us a little bit of room for error. And we always want to leave just a tiny bit of room for error because there's always error no matter what you do. All right, so that's that one. We'll move on to the next one. Okay, up next, step number 1, what do we do first? We balance the equation. So, okay, we have 4 nitrogen. We have 2 here and 2 here. We have 4 hydrogen and we have 4 oxygen. That's a lot of 4s. Over here we have 2 nitrogen, we have 2 hydrogen, and we have 1 oxygen. You can already see we're probably going to have to do something with that oxygen because it's a 1 and we need even numbers. So let's see what else we have to do. So we have 2 nitrogen, but I'm going to wait on the nitrogen because the nitrogen is single. All right, 4 hydrogen and 2 hydrogen. So I'm going to try putting a 2 here. That 2 changes this to a 4 and this to a 2. Well, that gives us enough hydrogen, but that does not give us enough oxygen. So I'm going to change that from a 2 to a 4 and see if that helps. So now we have 4 times 2 is 8 hydrogen, and we now have 4 oxygen. So over here on the left, we've got the 4 nitrogen, and on the right, we have 2 nitrogen, but we're waiting on nitrogen. Over here, we have 4 hydrogen on the left and 8 hydrogen on the right. So we need 8 hydrogen. So we're going to multiply this one by 2. And I'm glad we waited on that nitrogen now. So now we are going to change those to nitrogen is 2 times 2 is 4, plus these 2 is 6. And then we have the 8 hydrogen. So now we have 6 nitrogen, 8 hydrogen, and 4 oxygen. And over here we have 2 nitrogen, 8 hydrogen, and 4 oxygen. And we're just going to need to put a 3 here to change this to a 6. Always go back and double check. So we have 2 times 2 is 4, plus 2 is 6 nitrogen. 2 times 4 is 8 hydrogen, and 4 oxygen. 3 times 2 is 6 nitrogen. 4 times 2 is 8 hydrogen, and 4 times 1 is 4 oxygen, so this is balanced. So that is balanced. We're going to erase all this so we can put the information from the question in there. Hopefully on the test I'll leave you enough room. Actually, we're going to be taking tests on Blackboard this semester, so we'll see. So, oh, I just did that part. Geez. There we go. All right. So how many grams of nitrogen, so we're going to put a question mark here with a G, how many grams of nitrogen forms when 1.00 times 10 to the 2 grams of excuse me, dinitrogen tetrahydride. So why would they write it like this? Or why would I write it like this? Because I could do 100 point, and that would be 3 sig figs. But this is also showing me that I want 3 significant figures. So 3 sig figs. So this is just 100 grams, and you don't have to write it like that. Just know that you have 3 sig figs when you come back. So 100 grams of dinitrogen tetrahydride is mixed with 200 grams of N2O4. You can keep it in scientific notation if you prefer. So what type of problem is this? We have information about 2 different reactants and we're asked about a product. So this is a limiting reactant problem, which means 2 mass-to-mass problems. I want you to pause this and try this on your own, please. If you haven't done that yet, you really need to be doing these on your own. So pause the video and try it, and then let's see how we can do together at the end. So I'm going to keep going. You pause it. Pause it. Hey, I'm talking to you. Pause it. All right. So starting with 100 grams of the dinitrogen tetrahydride, so 100 grams of N2H4. I need the molar mass of N2H4, and I got 32.052 grams of N2H4 for every 1 mole of N2H4. I need the mole ratio step. I want to go from moles of this to moles of the question mark. So I have 2 moles of N2H4. I'm going to produce 3 moles of nitrogen. And then for every 1 mole of nitrogen, the molar mass of nitrogen is 28.02 grams. So when I do that on my calculator, I get 131.130667 grams. Go down to the 200 grams of N2O4, so dinitrogen tetraoxide. And that's going to be heavier, so 92.02 grams of N2O4 for every 1 mole of N2O4. Mole ratio here is I need 1 mole of N2O4 to produce 3 moles of nitrogen. And again, we're always going to the question mark. And every 1 mole of N2 has a mass of 28.02 grams of N2. When I calculate that in my handy dandy calculator, I get 182.699,413.2 grams. So in this question, the first question asks us, or might be the only question, the first question here is going to be how many grams of nitrogen form? So how many grams of nitrogen can form? We need to find what is the limiting reactant. So the limiting reactant is going to be N2H4. The excess reactant is then N2O4. If this is limiting, how did I know it was limiting? Because 131 is less, so it's limiting. This is our excess reactant, which is the reactant is actually that. So that means the amount that could be formed would be to the proper number of significant figures, 131 grams of nitrogen. So this one, we're not asked about the excess reactant, so we can move on to the next problem. So this one kind of has everything involved in it. I really, really want you to pause the video and try this one if you have not already done any of these, especially if you haven't done any of these already. Please pause the video and try this, okay? It's already balanced because we balanced this one earlier in the PowerPoint. So calculate the amount of water. How much water will be formed if 54.6 grams of C2H4 reacts with 235 grams of oxygen. All right, so starting with 54.6 grams, this is a limiting reactant problem of C2H4. I need the molar mass, so 28.052 grams of C2H4 for every 1 mole of C2H4. Do the mole ratio now. So 1 mole of C2H4 will produce 2 moles of water. And every 1 mole of water has a mass of 18.016 grams of water. That gives us 70.132, 15457, I think, grams. And we do it again, but we start with the oxygen. 235 grams of O2. There are 32 grams of O2 for every 1 mole of O2. Every 1 mole, every 3 moles of O2, because of the 3, is going to produce 2 moles of water. And 1 mole of water has a mass of 18.016 grams of water. And that comes out to be 88.20333 repeating grams. So which of these is smaller? This is smaller. So calculate the amount of water that can be formed. 70.1, because there's 3 sig figs, grams of water can be formed. From our limiting reactant, which is C2H4, the excess reactant then will be whatever this one is, O2. And now we need to calculate how much excess is left over. So this is where we go and we talk theoretically. If all of this oxygen would have reacted, we could have produced 88.2 grams of water. But we didn't produce it. We only produced 70.1 grams of water, giving us a difference of 18.1 grams that didn't form. I know that's such a weird, grams of water did not form. So we're going to go backwards and figure out how much that 18.1 grams of is in terms of oxygen. So 18.1 grams of water, what does that equate to in oxygen? Well, we're going to go just backwards of this problem here. So 18.016 grams of water for every 1 mole of water. All right, now we need the mole ratio. Remember, everything's just going to be upside down and backwards, but follow the units and you'll put everything in the right spot. So I need 2 moles of water from 3 moles of oxygen. And 1 mole of oxygen has a mass of 32 grams. So when we put that in our calculator, we get 48.22380,107 grams, or how much of the oxygen remains would be 48.2 grams of oxygen remain. How'd you do? That was a big problem. Hopefully you did well. If not, let's keep trucking. We'll keep doing some more practice together, and then there's lots of practice on Blackboard and Google. Search limiting reactant problems. Mr. Gooch, don't forget about Mr. Gooch. Mr. Gooch's Cavalcade of Chemistry has a lot of resources with answer keys, so that would help you. So let's do this one and let's balance it. We have 4 oxygen and 1 nitrogen, and over here we have 4 oxygen and 1 nitrogen. Woohoo, it's balanced! Yay! We don't have to do anything. Hot dogs. So they're all just a 1-to-1 mole ratio. So if 0.740 grams of ozone, O3, reacts with 0.670 grams of NO, how many grams of NO2 will be produced? Mass to mass problems, I'm going to have to write small. I didn't leave a lot of room. 0.740 grams of ozone. Right? The mass of ozone is 48 grams of O3 for 1 mole. And then we do the mole ratio, which is 1 to 1. So 1 mole of O3 will produce 1 mole of NO2. And 1 mole of NO2 has a mass of, what was it? Just calculate it. 46.01 grams. So my calculator gave me 0.7093208.333 grams. I do the same with the NO. 0.670 grams of NO. The molar mass of NO is 30.01 grams of NO for 1 mole of NO. 1 mole of NO yields 1 mole of NO2. And 1 mole of NO2 has a mass of 46.01 grams of NO2. It gives us 1.027214262 grams. So the question is, how many grams of NO2 will be produced? We have to answer that question first. This is our limiting because it's smaller, so smaller one. After we produce 0.079 grams, so 0.709 grams of NO2. Once those are produced, we run out of that material. So we run out of ozone. This is our limiting reactant. This will be our excess reactant. And we can't make any more product. Now, how much excess reactant remains? Well, we could have produced 1.03 grams, but we only produced 0.709 grams, leaving us with 0.321 grams that did not form. So that's grams of NO2 at this point. We need to bring that back to NO. So starting with 0.321 grams of NO2, we go backwards on this one and we find out how much NO that is. So 46.01 grams of NO2 for 1 mole of NO2. 1 mole of NO2 produces 1 mole of NO. We'll use this actually. And that 1 mole of NO has a mass of 30.01 grams, giving us 0.209372093, or with 3 sig figs, 0.209 grams of NO remain, or are left over. All right, I hope this is going well for you. I know this is a lot of math, but you know what? I know some of you really like math, so that's good. We're back in your wheelhouse. Few more terms, just a reminder of theoretical and actual yield. Theoretical is always predicted by stoichiometry. This is what we've been calculating. It's always calculated. Actual yield, you're going to have to be given this on a test. This is what you obtain, or you would find it mathematically in the lab. So you would measure it out or subtract until you find it. Whatever you're doing with your results, you're going to get this from experiment. So percent is the ratio of them. So it's actual over theoretical times 100. And I know we just went over that not too long ago, so I'm just going to let that go. Just a few slides ago. This is just a reminder slide of these terms. So we're going to start throwing theoretical yield in there into these problems. Let's take a look. A student reacts 3.75 grams of zinc with excess hydrochloric acid and produces 6.58 grams of zinc chloride. What is the percent yield? So I think one of the more difficult things for most students at this point is we're going to be given a third number. So you're actually given this, and that's not part of your math to get there. That's your actual yield. So you have to be able to pick that out in this story type problem. Also, I didn't give you an equation. So you're going to have to um, write and balance this equation, which we haven't really done a whole lot of yet. So zinc reacts with hydrochloric acid to produce zinc chloride. Well, zinc is a 2 plus cation and chloride is a 1 minus anion. So what is the formula? Because remember, we have to get the formulas right before we can get the balanced equation. So that would be ZnCl2 plus, now a couple ways that you should know that this other product is there even though it's not mentioned is I've told you anytime you react a metal with an acid, you're going to get this product, but also what's left over is going to be the hydrogen, so H2. So when we go to balance this, we're going to need a 2 here to balance this equation. Hopefully you can go through that and figure that out. Now we're saying we have 3.75 grams of zinc. We have excess hydrochloric acid, so I don't have to do a limiting reactant problem. I just have to figure out what the theoretical yield or the grams of zinc chloride that could be formed if I react 3.75 grams with um, excess hydrochloric acid. So I didn't leave a lot of space on this slide, so I'm going to try to erase that. But I'm getting better though, hopefully. All right, so 3.75 grams of zinc. The mass of zinc is 65.41 grams of zinc for 1 mole, just from the periodic table. And in this problem, 1 mole of zinc is going to give us 1 mole of zinc chloride. And 1 mole of zinc chloride has a mass of 136.31 grams of zinc chloride, giving us 7.814745 for something grams. So 3 significant figures. My theoretical yield is 7.81 grams of zinc chloride. So I now have the theoretical. I calculated this. This was given in the problem, and now I can calculate the percent yield. Oh, I want to actually calculate that. Let me just change colors. So I take the actual value, 6.58 grams, divided by the theoretical, which in this case is 7.81 grams times 100. And when I do that, I get 84.20, no, 25, sorry, 250.96031, or 84.2% yield. And this is actually a 2 because this should be a 1. Sorry, I want to fix that slide. All right. So that is how you calculate percent yield, and make sure we're practicing writing and balancing equations because you do know how to name things. So we're going to have to keep practicing. All right, we're going to keep trucking. Got a lot of problems to do. Again, theoretical yield is always calculated. We have to calculate that one. Actual yield is going to be measured, so it's going to be given on a test, on a paper test. In lab, you will find it. So it's determined from experiments. Here we go. We already used this equation, so it's balanced for us. Calculate the theoretical yield of copper. So how many grams of copper can be produced when 85 grams of oxygen reacts with excess copper 1 sulfide? So not a limiting reactant problem. We just have to go through it once. 85.0 grams of oxygen. There are 32 grams of oxygen for 1 mole of oxygen. And in the balanced equation, we have 1 mole of oxygen is equivalent to 2 moles of copper. And those coppers each have, so every 1 mole of copper has a mass of 63.55 grams, giving us an answer of 337.609375 grams, or 338 grams of copper that could be produced. This is our theoretical yield. Once I have the theoretical yield, this says if 231 grams of copper are obtained, this means it's our actual yield. It's usually smaller as well. 231 grams divided by 338 grams that we could have produced times 100 gives us a percent yield of 68.34319527 grams. It's not always great, so 68.3% yield. Some equations, some chemical processes don't give great percent yields, but that doesn't mean we don't do them. It just means we have to do them in higher quantities to get more of what we need. That is unfortunately the reality for some things, and we can figure out how to get more of what we need is the way to improve the process. Again, here we go. Let's balance. We have 1 aluminum, we have 1 hydrogen, and 1 Br. 1 aluminum, 2 hydrogen, and 3 Br. Well, where do we start? I'm not going to start with hydrogen because that's by itself, so I'm actually going to start with the bromine. So let's put a 3 here. That changes this to a 3 and this to a 3. Well, now I have a problem because I have an odd number here and an even number here. So the only way to get rid of this odd number is actually multiply it by 2. So let's try that. Instead of having 3, let's try 6. So 6 HBr gives us 6 hydrogen and 6 bromine. Now over on this side, I only have 3 bromine, so I'm going to try putting a 2 here. That makes it 2 aluminum and 6 bromine. So that will give me a 2 here for 2 aluminum. And I have 6 hydrogen and 2 hydrogen, so I need a 3 here to give us 6 hydrogen. Right. Hopefully this is getting easier. It's probably a little bit more tricky, this one, than the ones that we've been doing. So 2 times 1 is 2 aluminum. 6 times 1 is 6 hydrogen. 6 times 1 is 6 bromine. 2 times 1 is 2 aluminum. 2 times 3 is 6 bromine, and 3 times 2 is 6 hydrogen, so this is balanced. Okay, let's take a look at the problem, see what we're asked to do. Calculate the theoretical yield of aluminum bromide. So how many grams of aluminum bromide will form when 20 grams of aluminum react with excess HBr? Now, we just did a ton of limiting reactant problems, so I'm being a little bit nicer to you right now and telling you which one is limiting. But in theory, and most likely on any test, I will have you do all of it in one problem. So you'll get down to the bottom of that limiting reactant problem, and it'll just give you an actual yield and ask you what the percent yield is. So 20 grams of aluminum. All right, so the 20 grams of aluminum has a mass of 26.98 grams of aluminum per 1 mole of aluminum in the periodic table. Mole ratio says that 2 moles of aluminum are going to produce 2 moles of aluminum bromide. And the aluminum bromide, so 1 mole of aluminum bromide, has a mass of 293.69 grams. My calculator says that that is 217.7094144. So what is the theoretical yield? Let me just double check that. So I'm going to put that in my calculator. It's 20 divided by 26.98 times 2 divided by 2 times 293.69 and 217.709. Yep. So this would be to 3 significant figures, 218 grams of aluminum bromide. That's our answer to this part. Number unit label, sig figs. Now down here, if this is our actual yield, if we actually got 175 grams of aluminum bromide and we could have gotten 218 grams, what was our percent yield? So 175 divided by 218 gives us 80.275 to 2936 or 80.3% yield. And that percent is your unit, so or your sorry, yeah, your unit. So make sure you have that in there. One more problem together. So F8 plus Cl2 gives us S2Cl2. We need to balance this. So we have 8 sulfur, 2 chlorine over here, and we have 2 sulfur and 2 chlorine. I'm going to guess we need a 4 here. That'll make that 8 and that 8. And then we put a 4 here, and now we have 8 and 8, and it's balanced. All right, so let's extract the information from the problem. What is the theoretical yield of S2Cl2? So remember, that's always in grams. So how many grams? Well, it actually says in grams. When 4.06 grams of S8 are heated with 6.24 grams of Cl2. This is a limiting reactant problem. So 4.06 grams of S8. S8 has a mass of 256.56 grams of S8 for 1 mole. 1 mole of S8 yields 4 moles of S2Cl2, and 1 mole of S2Cl2 has a mass of 135.04 grams. Notice I am not rounding off these molar masses, and you should not as well. 8.54790146 grams. 6.24 grams of Cl2. Cl2 has a mass of 70.9 grams for 1 mole. 4 moles of Cl2 are going to produce 4 moles of S2Cl2, and every mole of Cl2, S2Cl2, has a mass of 135.04 grams of S2Cl2. And that gives us 11.88504372 grams. Theoretical yield is going to be the smallest because this is our limiting reactant. So 8.55 grams of S2Cl2 is our theoretical yield. So if 6.55 grams actually formed, and we could have formed 8.55 grams, what is our percent yield? We get 76.60818,713, or 76.6%. Good, lots of math today. I hope you're doing well with it. We got a lot more math coming up, so we're going to take a little break on this video here, and I'll come back with another one with lots more math for your pleasure. Hope you're having fun.